Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion regarding the efficient framework for generating shared random multiplication triples. So, in the last lecture we had seen the triple transformation protocol. In this lecture we will complete the analysis of the triple transformation protocol. So, just to quickly recap, what are the required properties from the triple transformation protocol? The input will be a set of 2D plus 1 number of secret shared triples, and these triples need not be multiplication triples, and there may not be any relationship among these triples, and all these triples are shared triples, shared as per the sum is secret sharing, where the degree of the sharing is t, and here d will be at least t. And the output for the triple transformation protocol will be another bunch of 2D plus 1 secret shared triples, which are now correlated, and the correlation are the following. So, first of all, we want that the A components of all the output triples, they should lie on a d degree polynomial. All the B components of the output triples should lie on a d degree polynomial, and the C component of all the output triples should lie on a 2d degree polynomial. So, I stress that the A component, B component and C components of the output triples, they are themselves secret shared, but we want that the values of those triples, they should lie on polynomials A, B and C of degree d, d and 2d respectively. That is the first correlation we require from the triple transformation protocol. The second correlation that we require is that the C polynomial should be equal to the product of the A and B polynomials if and only if all the input triples are multiplication triples, and this should hold in an if and only if fashion. Namely, if the C polynomial is the product of A polynomial and B polynomial, then that implies that all the input triples were multiplication triples and vice versa. That is, if all the input triples were multiplication triples, then the C polynomial is the product of A polynomial and B polynomial, which implicitly means that all the output triples are also multiplication triples. And the third property from the security point of view is that if the ith input triple was random for the adversary, then the ith output triple should also be random for the adversary. Of course, adversary will have t shares for each of the triples, both for the input triples as well as for the ith triple, but the property here demands that if the ith input triple was random, namely the value of the triple was unknown to the adversary, then the value of the ith output triple also should be unknown to the adversary. So, these are the requirements from the triple transformation protocol, and in the last lecture we had seen a protocol for triple transformation. So, let me quickly go through the steps of the triple transformation protocol. So, what we do is that we are given 2d plus 1 number of secret shared triples. So, this is the input, and that input, the input triples are divided into two groups. The first group consisting of d plus 1 number of triples. So, sorry, pardon here, this the input is only this in the picture, and this is the output. So, the idea behind the protocol is that we divide the input triples into two groups. The first group consisting of the first d plus 1 secret shared triples, and then the second group has the remaining d secret shared triples. Now, using the first d plus 1 secret shared triples, we do the following: we define the A and B polynomials. So, we let the A polynomial to be the unique d plus 1 degree, unique d degree polynomial, passing through the A components of the first d plus 1 input triples, and then that automatically defines that automatically sets the first d plus 1 output triples as well. So, the first d plus 1 output triples are set to be the first d plus 1 input triples, and then we compute new points on this defined A polynomial in a secret shared fashion, because that involves of computing linear function. So, we compute the next set of points on the A polynomial, and they constitute the remaining d output triples. So, since these points can be computed as a linear function of the first d plus 1 points on the A polynomial, all of which are secret shared, it follows from the linearity property of secret sharing that the parties can now compute a secret sharing of the A components of the remaining output triples. The same thing we do even for the B polynomial. We take the B components of the first d plus 1 triples, and using those as the distinct points we define a d degree polynomial, and then we compute the next set of points on that defined B polynomials, and this will help the parties to locally compute the secret shared B components of the output triples. And now what we do for the C polynomial is the following. We take the leftover d number of input secret shared triples and use them as the auxiliary triples in the Beaver's method to compute the C component of the last d output triples, and now we have 2d plus 1 number of C components for the output triples. Using them we define the C polynomial. So, that was the protocol, and now we want to prove that it achieves this triple transformation protocol achieves all the properties that we had desired for. Okay. So, the first claim here is that the A polynomial that we have defined is a d degree polynomial such that the A component of all the output triples lie on this A polynomial, and this simply follows from the steps of the protocol. How exactly we have computed the A component of the output triples? Well, the first d plus 1 the A component of the first d plus 1 output triples are same as the A component of the input triples, and the A component of the last d output triples are distinct points on the A polynomial. Okay. So, that comes from the steps of the protocol. The proof is straightforward. The similar claim we can make for the B polynomial. The claim here is that the B component of all the output triples lie on a d degree B polynomial, and this again comes from the steps of the protocol. The B component of the first d plus 1 output triples are same as the B components of the input triples. Using them we define the B polynomial, and this B polynomial will be a unique polynomial, because using d plus 1 distinct points we can only define a single d degree polynomial, and then the remaining points on the B polynomial constitute the B component of the last d output triples. And then we have the claim that the C component of all the output triples lie on a 2d degree C polynomial, and this also follows using a similar argument because of the steps of the protocol, namely the C component of the first d plus 1 input triples are set to be the C component of the first d plus 1 output triples. And now we are applying the Beaver's method to compute the C components of the last d triples, and now using the C component of all the output triples, which are 2d plus 1 in number, we are defining the C polynomials. So, using 2d plus 1 distinct points we can define a unique 2d degree polynomial, and that polynomial in this case is the C polynomial. So, all these 3 claims hold. Now, let us prove some other properties. So, we next claim here that for each of the triples, namely for I equal to 2d plus 1, if the ith input triple was a multiplication triple, then the ith output triple is a multiplication triple and vice versa. Okay. And this holds for any I in the range 1 to 2d plus 1. So, let us take some arbitrary I in the range 1 to 2d plus 1. So, the claim is obviously true if that I is in the range 1 to d plus 1, because the first d plus 1 output triples are set to be the first d plus 1 input triples. So, if the first d plus 1 input triples are multiplication triples, then that automatically implies that the first d plus 1 output triples are also multiplication triples. So, the claim is obviously true if my I is either 1 or 2 or d plus 1, but my I could be different from 1 to d plus 1, because remember the way I have computed the output triples is that I do some set of actions for the first d plus 1 output triples and a different set of actions for the last d output triples. So, what I have argued here is that if I focus on the first d plus 1 output triples, they will be multiplication triples if and only if the first d plus 1 input triples are multiplication triples. Now, consider an I in the range d plus 2 to 2d plus 1, namely a triple which is different from the first d plus 1 output triples. My claim, I would like to claim that even that output triple will be a multiplication triple if and only if the corresponding input triple was a multiplication triple. So, for that we have to show that the Ci which we have computed, the C component of the output triple, is the product of the A and B component if and only if for the ith input triple the C component was the product of the A component of the input triple and the B component of the input triple. Now, for that we have to see how exactly we have computed the C component of the ith output triple. We have computed the C component of the ith output triple by applying the Beaver's method on the A component of the ith output triple and the B component of the ith input triple, and for applying the Beaver's method we have used the ith input triple as the auxiliary triple. Now, as part of the Beaver's method, what exactly are the computations which are involved for computing the C component of the ith output triple? Well, we would have computed an intermediate value u and intermediate value v and would have publicly reconstructed them. The values u and v would have been robustly reconstructed even if up to t parties produce incorrect shares, because we are in the setting of t less than n over 3, and that is why the error correction will work properly. So, that means everyone will reconstruct the right value of ui and vi and then as per the Beaver's method the C component of the ith output triple would be set to this value. Now, this value will be same as the product of the A component and B component of the ith output triple if and only if the C component of the ith input triple was the product of the A component and B components of the ith input triple. Okay. And that shows that this claim is now true even for an output triple where that output triple is in the range d plus 2 to 2d plus 1. Okay. So, we have proved a bunch of claims now. We have proved the claims regarding the degrees of the A, B and C polynomial, and we have proved that the ith output triple is a multiplication triple if and only if the ith input triple was a multiplication triple. Now, as a corollary of all these claims, as an implication of all these claims, we can claim that the C polynomial is the product of the A and B polynomial if and only if all the input triples are multiplication triples. This is because the C polynomial is a 2D degree polynomial, A polynomial is a D degree polynomial, and B polynomial is a D degree polynomial. Okay. So, let us prove this implication. So, since it is an if and only if statement, we have to prove two things. So, the first thing we have to prove is that if the C polynomial is the product of the A and B polynomials, then all the input triples are multiplication triples, and that comes from this claim. Because if the C polynomial is the product of A and B polynomials, that means the C component of all the output triples is equal to the product of the corresponding A component and B component of the output triples, because the points because the A, B and C components of the output triples, they lie on the A, B and C polynomials, which followed from the first two claims. And now, if the C component of every output triple is the product of the corresponding A and B components, then because of this last claim, it automatically follows that even for the input triples, the C component is the product of the A and B component. So, that shows the implication in one direction. The other direction thing that we have to prove is that if all input triples are multiplication triples, then we want to claim that C polynomial is the product of A polynomial into B polynomial, and this again comes from the fact that if all the input triples are multiplication triples, then from this third claim, this last claim, all the output triples are multiplication triples, and the output triples are nothing but the points on the A, B and C polynomials, and C polynomial has degree 2D and A and B polynomials have degree D, which automatically implies that the C polynomial will be the product of the A and B polynomials. Now, let us prove the last property which we require from the triple transformation protocol. The property that we require is that if the ith input triple was random for the adversary, random in the sense it does not know the value of A component, B component and C component, except that the C component is the product of A and B component. That means that triple could be any triple over the field. Then at the end of the triple transformation protocol, even the ith output triple is also randomly distributed for the adversary. Adversary will not know the exact value of the ith output triple. It could be any triple over the field corresponding to which it may have at most T shares. So, again, to prove the claim, we have to focus on the index I, and there could be two cases depending upon whether the ith triple is one of the triples among the first D plus 1 output triples, or whether the ith triple is one of the triples among the last D output triples. So, if this I is in the range 1 to D plus 1, then the claim holds trivially, because of the way we have defined the first D plus 1 output triples. The first D plus 1 output triples are said to be the first D plus 1 input triples. So, if any of the triples among the first D plus 1 input triples is random for the adversary, then that automatically implies that the same triple is, when viewed as an output triple, is also random for the adversary. Because for computing the first D plus 1 output triples, we have not done any computation. They are said to be the first D plus 1 input triples only. Whereas, consider the case where I is in this range D plus 2 to 2D plus 1. Okay. So, in this case, what can we say about the A component of the output ith output triple and the B component of the ith output triple? Well, they are computed non-interactively. Why they are computed non-interactively? Because they are basically locally computed as a distinct point on the defined A polynomial and as a distinct point on the defined B polynomial, and this does not require any interaction among the parties. So, if there is no interaction happening among the parties, that means adversary has learned nothing about the resultant A component of the ith output triple and the B component of the ith output triple. But for computing the C component of the ith output triple, interaction is involved, because the C component of the ith output triple is computed by applying the Beaver's method, where the ith input triple is used as the auxiliary triple. So, now let us go into the details of what exactly are the computation involved for computing the C component of the ith output triple. For computing the C component of the ith output triple, the parties would have reconstructed two public values, namely the value ui and value vi, by exchanging shares and applying the Reed-Solomon error correction. But as per our assumption, the ith input triple is random for the adversary, because that is the hypothesis of the claim statement. So, if the ith component of the if the A component of the ith input triple and the B component of the ith input triple, they are random for the adversary, then even though the adversary would have learned the values ui and vi, it cannot figure out what exactly is the value of the A component of the ith output triple and the B component of the ith output triple, because ui and vi will serve as the one time pad encryption of the A component and B components of the ith output triples respectively, where the pads are random. The pads here are the A component and the B component of the ith input triples, and that shows that the probability distribution of this ui and vi values which adversary would have learned will be independent of the A and B components of the ith output triples. Okay. And finally, the C component of the ith output triple is computed locally once the values ui and vi are publicly known. Hence, adversary does not learn anything additional about the C component of the ith output triple. It is a randomly distributed value. Okay. So, that is all about the triple transformation protocol. That means, we have now proved all the desired properties of the triple transformation protocol, namely the protocol takes a bunch of unrelated triples which may or may not be multiplication triples and transform them into another bunch of correlated triples, okay, in a very nice way, and the correlation is very nice. Namely, the correlation is that the A, B and C components of the output triples now constitute distinct points on some well defined A polynomial, B polynomial and C polynomial, such that the C polynomial will be the product of A and B polynomials if and only if all the input triples are multiplication triples. And I stress here that here all the computations are performed over secret shared values. So, for the input triples, the values may not be known to any party, they might be secret shared, and even for the output triples, the values may not be known to any specific parties, but all of them are in secret shared fashion. That means, even the polynomials A, B and C are also not known to any specific party, but they are in a secret shared fashion. That means, every point on the A polynomial, B polynomial and C polynomial is actually available in a secret shared fashion. And all this is happening because we are exploiting the linearity property of secret sharing here. So, with that I end this lecture. The reference for this lecture is this paper. Thank you.